Hey everyone, welcome back to the channel. Today, I'm incredibly excited to take you on a journey into the fascinating world of quantum mechanics guided by one of the greatest scientific communicators of all time, Richard Feynman. Watching the electrons from Richard Feynman's Lectures on Physics, Volume 3, Chapter 1. Feynman, who made quantum mechanics fun, takes us on a wild ride with this experiment. Get ready to have your brain stretched. Stick around, subscribe, and let's explore this quantum world together. Let's go. Picture this. We've got an electron source. Think of it like a tiny gun shooting electrons. Those electrons hit a barrier with two slits, and behind it, a detector screen catches where they land. The big questions. Do electrons act like bullets or waves? Feynman set up this classic double-slit experiment to find out. What happens when we fire these particles? Classically, we'd expect them to behave like tiny bullets, passing through one slit or the other, creating two distinct bands on the screen behind. But quantum mechanics has a notion for us. Now let's imagine electrons are just like bullets. If they go through one slit or the other, we'd see two distinct bands on the screen. Simple, right? That's classical physics, predictable and intuitive. Classical physics, predictable and intuitive. Well, it's pretty straightforward. Each electron would go through either the left slit or the right slit, never both. And as they hit the screen, they would simply pile up directly behind each slit, creating two distinct bands of impacts. You can see that here, a clear indication of individual particles hitting a target. This is exactly what you'd observe if you were firing paintballs, for example. Two clear lines, one for each opening. Simple, right? But as we'll see, the quantum world has a much more intriguing story to tell. Here's the kicker. Feynman shows us nature doesn't always play by those rules. Let's see what happens next. But now let's consider a very different possibility. What if, instead of discrete particles, our electrons were behaving like waves? If waves encounter two slits, something remarkable happens. They interfere with each other. Where wave crests meet crests, they reinforce, creating a stronger wave. Where crests meet troughs, they cancel out. On our detection screen, this wave-like behavior would manifest as an interference pattern, a series of alternating bright and dark bands. The bright bands are where the waves reinforce, and the dark bands are where they cancel out. This is a telltale sign of a wave behavior, something no classical particle could ever produce. Electrons, tiny particles, are acting like waves. Feynman's telling us the quantum world is full of surprises. Stay tuned to see why. Now here's where the experiment gets truly mind-bending. What happens if we try to watch which slit each electron goes through? We might place a light source or a detector right next to the slits, essentially trying to see the electron. When we do this, and we introduce an observer to try and pinpoint the electron's path, something extraordinary happens. The interference pattern, those beautiful wavy bands we saw when the electrons behave like waves, disappears. Instead, what we observe is exactly what we'd expect from classical particles. Two distinct bands, as if the electrons suddenly decided to behave like tiny bullets again. It's as if the very act of observing forces the electrons to choose a path, collapsing its wave-like nature into a particle-like one. We are back to two bands, like particles again. Feynman shows us that watching changes the game. Quantum mechanics is all about observation. So how do we make sense of this bizarre behavior? How can electrons seem to be both waves and particles, and how does observation change their behavior? This is where Feynman's genius and the concept of probability amplitudes comes into play. In quantum mechanics, we don't say an electron is a particle or a wave in classical sense. Instead, we say it has a probability amplitude to arrive at a certain point. Think of it this way. When an electron leaves the source, it doesn't just have a probability of going through a slit A or a slit B. It has a probability amplitude for both paths simultaneously. These amplitudes, like waves, interfere with each other. The interference pattern we see on the screen is the result of these probability amplitudes adding up or cancelling out for all possible paths an electron could take. When we observe which slit the electron goes through, we are essentially forcing it to collapse into a definite state, eliminating the possibility of it taking both paths and thus eliminating the interference. It's a fundamental shift from thinking about where it is to where it could be and with what likelihood. Here's the paradox. Electrons are neither just particles nor waves, they're both, depending on how we look. Feynman famously said, "Nobody understands quantum mechanics. It's about probabilities, not certainties. So don't ask how. Just predict what happens." Quantum's weird, and that's okay. In other words, this brings us to what Feynman famously called the only mystery of quantum mechanics, the heart of the enigma. The double-slit experiment, in its elegant simplicity, lays bare the profoundly counterintuitive nature of reality at the smallest scales. Electrons, and indeed all quantum entities, do not behave like classical objects. They don't simply choose a path, nor are they simple waves that spread out. They exhibit both particle-like and wave-like characteristics depending on how we observe them. This isn't just a technical detail. It challenges our very classical understanding of cause and effect, of certainty, and even what constitutes reality. Feynman himself, with his unparalleled intuition, didn't try to explain why it happens in a classical sense. Instead, he famously advised, "Shut up and calculate." The mystery isn't that we don't know how to describe it mathematically. We do, with incredible precision. The mystery is that our everyday intuition simply cannot grasp what's truly happening at the quantum level. It demands a new way of thinking, a new conceptual framework, which is what quantum mechanics provides. So, as we bring our exploration of these foundational ideas from Feynman's lectures to a close, let's distill some key takeaways. First, the wave-particle duality. Electrons, and indeed all quantum entities, exhibit characteristics of both waves and particles. They are not one or the other exclusively, but rather possess this dual nature. Second, the influence of observation. The act of measuring or observing a quantum system fundamentally alters its behavior. Trying to determine an electron's path changes its outcome, forcing it to act like a particle. Third, probability amplitudes. Quantum mechanics doesn't deal in certainties, but in probabilities. Feynman showed us that particles move according to probability amplitudes that interfere with each other, leading to the observed patterns. And finally, a crucial point emphasized by Feynman: embrace the mystery. The quantum world defies our classical intuition. Rather than struggling to feed into our everyday experience, we learn to describe it mathematically and accept its inherent strangeness. It's a different kind of reality, and understanding it means accepting that fundamental difference. You might be thinking, this is all fascinating, but why does it matter? Why should I care about electrons acting strangely through tiny slits? The truth is, understanding this fundamental quantum behavior isn't just an academic exercise, it's the bedrock upon which our modern technological world is built. From the ubiquitous computer chips in every device you own, which rely on the quantum properties of semiconductors, to the precision of lasers used in everything from barcode scanners to fiber optics. Think about MRI machines in hospitals performing non-invasive medical imaging by leveraging nuclear magnetic resonance, a purely quantum phenomenon. Even the development of quantum computing, which promises to revolutionize computation as we know it, stems directly from harnessing these very principles of superposition and entanglement. Beyond technology, understanding quantum mechanics reshapes our philosophical view of the universe. It tells us that reality at its most fundamental level is far stranger, more probabilistic, and more interconnected than we ever imagined. It expands our minds and encourages us to question our assumptions about the very nature of existence. This isn't just physics, it's a profound insight into how the universe actually works.